38, 40. Next, 42, 44. 42, 44, 46. 48.
Yes, sir.
Is there anyone left from section A2?
517, sir.
Yes, you can write your ID, please. Next, from section C2, right? Three 14, 316. 26, 326, 328, 32, 34. Continue. (44, 46, 48). So anyone else left who have not given the attendance?
Sir, I am 116.
Yeah. You can write your ID now. Okay, so let's start.
Sir, I was 314, sir. I had to break the serial because my enter was
all
not
right.
being registered.
Okay, so can you see the screen?
Yes,
Sir,
sir.
it's black, sir. Yes.
So
Now it's okay.
this is your numerical methods. Okay, math 4522 is based on 4521 numerical methods. It's currently taken by Ruhulami sir probably. So this is a weekly lab. Okay, so in total there are 12 experiments, and each week we'll try to cover one experiment. Okay. And the credit is 1.5 credit, not 2 credit. It is 1.5 credit course, like your software and hardware lab. It is entirely software, so total 12 experiments. Okay. So let's start with the first experiment today. I'll provide you the lab manual. So you can see the first experiment is sources of error for numerical method. Now this lab is mostly done in MATLAB. You can also try in Python as well, but Python is not covered in the lab manual. You can try it by yourself. So I will. Anyone saying something? Okay, so let's start with the first experiment, that is sources of error. Sources of error in numerical methods. Let me give you a little bit of theoretical background, then we go to the code. Okay. Okay. Sources of error. The first type of error is true error. So what is true error? True error is your true value minus your approximated value. Approximation. Say for example, you are measuring a table. The true length of the table is, say for example, 10,000 centimeter. Okay. 10,000 centimeter. and you have calculated the error as 9,999 centimeter. Okay, so the error is 1 centimeter, right? The difference between these two, this is your
Yes, sir.
actual length and this is the length that you actually calculated somehow. So this is the error is 1 centimeter and this is known as true error, and it is represented as capital E subscript T. Now say for example in another experiment, the true length was 100 centimeter. Okay, and you have calculated the length as 99 centimeter. What is the true error now?
1 centimeter.
1 centimeter.
1 centimeter.
Okay, but the question is, are they same?
No, sir.
No, sir.
These two are not actually same, because in first scenario you have a error of 1 centimeter with respect to 10,000 centimeter. That is pretty small. But when
Yes.
you're making an error of 1 centimeter with respect to 100 centimeter, that is a bit larger. Okay. But both scenario you have a true error of 1 centimeter, right?
Yes.
Yes, sir.
So this is not the proper representation of what is the scenario. Okay. It is not taking into considering the order of the magnitude. It is not considering that. So what can I do about that? We can add a
Fraction.
new parameter that is known as relative true error. Relative true error. Okay. So it is equals to your true error that we just calculated divided by the true value. You divide this error that you calculated, the true error, with the true value. If we do that, what we get? So 1 centimeter divided by this 10,000 centimeter, right? 10,000
Yes.
represented as a percentage side, multiple by 100%. Written as percent for clarity. So the error is 0 point multiple by 100. We have 3 left. So 0.01%
001.
or something, 0.1001, something like that. In
Yes.
this scenario, what you have 1 divided by 100. So multiple by 100 again, 100%. So the error is 1%, right?
Yes.
Yes, sir.
So now as you can see, in this scenario, you have a 1% error, and this scenario you have made a 0.01% error. So this is too small. Okay. Now you can see from relative true error, you can actually understand the what you can say, the
Or the magnitude.
order of the the error, the kind of error that you are making. In this scenario, the error is too small, but in this scenario, we are making a larger error. Okay.
Yes. Yes.
Okay. So, any question from anyone?
No, sir.
Now the question is, the problem is that, so what is this true error? Sorry, what is this true value? What is this true value? Okay. Here I said that 10,000 centimeter is the true value, but in real scenario, in real world application, how do we actually know the true value? How can we know the true value? The thing is, most of the times we actually don't know the true value. Say for example, pi. Do we know the actual value of pi? No, we don't,
No, sir.
because this is the infinite. Okay, infinite. So we actually don't know, especially numerical methods. We'll see that we don't actually know the true value. We cannot find the true value. Okay. So what do we do about that? What can you do about that? So what can you do about that is that we take the best estimate. We take our best estimate. Okay. And we consider that best estimate as our true value. So for example, say for pi, start from 3.14159, okay, 159, go up to 15 digits, okay, go up to 15 digits after the decimal point, 15 digits, okay. We can consider this whole portion as our true value up to 15 digits, but that is not actually the true value. That is our estimate, the best estimate that we are making. Is it clear?
Yes, sir.
Now, in numerical methods, when you actually go further, you will see there is one is analytical approach, one is the numerical approach. Okay. Sometimes the analytical approach, the value you get from the analytical approach is considered as the true value. Okay. You will see that later. For now, just understand this, that true value is hard to get. Normally, we don't know the true value, so we use our best estimate as a true value. Okay. And we use that for our calculation. So two kinds of error. Let's see other two.
Sir, I have a question.
Yes, of course.
Sir, then what is the difference between the approximation and the true value?
Okay. The base, it is the best estimate. Okay. This is the best estimate. Approximation is our, I am trying to estimate. I am trying to get to the best estimate. The more I calculate, the more I iterate, I will try to go to the best estimate. For example, when I am calculating this phi, if I make a approximation of 3.149, I have to calculate, right? So if I make a approximation of 3.159, then the difference between these two is the true error, this whole 15 digits and this portion. You understand?
Okay, sir.
In this lab, we'll see a little bit later how to calculate this true error. Come here. Okay, number 3 is your approximation error. So what is the approximation error? That is the current approximation minus the previous approximation. Oh, one other thing. This is represented as epsilon of A. This one, relative true error, is epsilon of t. This is capital E of t. This is epsilon of t. Okay. Now, approximation error. So, numerical method, it is actually an iterative process. Okay, this is an iterative process. So we iterate to get to the better approach. We'll see it later on. So iterate means, say for example, from I is equals to 1, I try to go up to, say for example, 50. I iterate. Okay. The more I iterate, okay, the closer I get to the true value. So for example, for I is equals to 10, the result I get, if I iterate further, if I get I is equals to 20, I'll get a better result. Okay. So for example, in the 20th approximation, you have a result. So result equals to, say for example, P1. In the previous one, you had a result of P2. So which one will be better?
The P1.
P1 will be
Last
better
one,
because it is
latest
the
one.
further approximation that you made.
Yes.
The difference between these two, P1 minus P2, that is your approximation error. So how much improvement you are making, that is your approximation error. Okay. And you can also add something like this, phone number, that is the relative approximation error. Relative EA is equals to your approximation error EA, sorry, divided by your current approximation. This is your
Right.
EA,
EA stands for?
approximation error.
Oh,
E subscript A, that is the approximation error. Capital is E for error and E is for approximation. So that means the relative approximation error is
okay.
this P1 minus P2 divided by this P1. Okay. So this is the relative approximation error. It is also represented as a percentage. Also represented as a percentage. Okay. You will see how we can calculate all of those things a little bit later. Okay. Achha. Any question up to now?
No, sir.
There are two other types of error. Number 5 is the round off error. So what is round off error? In MATLAB, you have written an equation like this. Say for example, you have something like 2.678. Okay. This is, say for example, this is your true value. When you're writing in MATLAB, if you write like this way, round, say for example, this is the value A, comma 2. So this is your A. Okay. Round, this is the MATLAB built-in function. 2 means I want 2 digits after the decimal point. So So what this one will give 2.68, right? Because this is greater than 5. So when I am rounding it off up to 2 decimal points, it will just take if it is greater than 5, it will add 1 here. If it is less than 5, then it will keep it same. But these two are not same. Okay, there is a difference. So the difference is the round of error that you are getting. Is it clear now? Any question?
Sir, the difference is the round of error, sir.
Yeah. I cannot listen. I cannot hear.
I don't know, my internet is bad or it's from your end, sir.
Can you listen to me now?
Yes, sir.
Okay, I think my Wi-Fi was actually making it. Yes, my Wi-Fi was. I have to buy net package. Can you listen now? Okay, let's continue there.
Yes, sir.
Yes.
Okay. Did you see this part, the round of error?
Yes. Sir.
Yes, sir.
Can you repeat it?
Okay. So in the round of error, say for example, you have this value, or it
Sir,
can be.
sir, I can see your screen.
Okay. Sorry. I think share this screen again. Can you see it now?
Yes, sir.
Okay. So in the round of error, so say for example, you have a value like this, 2.678. You can round it off up to any decimal point that you want. Okay, 4, 3, 4, 5, 6, whatever you want. And when you are doing that, around a comma 2, that means you are rounding off up to 2 decimal point. Then you are having 2.68. And this one is not equal. There is a difference. Okay. The difference is known as round of error. Is it clear
So,
now?
if we have to calculate it, sir, what will the value of the round of error be?
0.0 or 0.0.
Just the difference, sir. There's a difference between
The difference between these two. Okay, that's the difference. Okay, so let's go to the final one. The fifth one. Okay, sixth one, right? This is the truncation error. Truncation error. Okay, so what is truncation error? Say you have a mathematical expression. For example, Taylor series. Taylor series. Do you remember Taylor series or Maclaurin series? You remember?
Yes, so we remember the Taylor series. Sir. Yes, little.
The Taylor series was an infinite sum of terms, right?
Yes,
Taylor
sir.
series, when you expand the series, you don't have to remember everything. It was an infinite summation. So
Yes.
the summation of I is equals to, or n is equals to, not I, we use n for that. For n is equals to 0 to infinite. So I'm summing up to infinite. Okay. What I'm summing? Okay. I'm taking the derivative, the nth derivative at point A. Okay. Divided by the factorial of n and x minus at this point to the power n. Don't worry, you don't have to remember the equation. The main point is this is the infinite series. Okay, for n is equals to 0, n is equals to 1, n is equals to 2, you have to keep adding these terms up. Okay, so for a is equals to 0, you have something like that. It's called Maclaurin series. Maclaurin series. let's say one series that is common one is e to the power x. Okay, exponential. So I want to sum up for n is equals to 0 to infinity, infinite. Okay, here a is equals to 0 for Maclaurin series. So x to the power n divided by n factorial. So if I expand that series, what will become? For n is equals to 0, x to the power 0 divided by 0 factorial plus x to the power 1 divided by 1 factorial plus x square divided by 2 factorial plus x cube divided by 3 factorial, and continuously going on and on, right?
Yes, sir.
Up to infinity. But can we calculate up to infinity?
No, sir.
We cannot. So what we'll get? We'll make a best approximation of this series e to the power x, and we calculate up to 1 that we can. Okay. Say for example, I can calculate up to this fourth term, n is equals to 3, that means 4. And the true approximation that was made up to, say for example, n is equals to 20.
Yes.
And I'm calculating up to n is equals to 3. Okay. So n is equals to 20. That was our best estimate. That is the true value. And that I am calculating, that is my approximation. The difference between these two is my truncation error, or you can say the true error. Is it clear?
Okay, sir. But sir, I don't know the infinite value. So how will I compare the two values, sir?
I will compare with the best approximate. N is equals to 20. The best I can.
Okay, sir.
So if I continue, because as you can see, there is a factorial inside in the denominator. So if you calculate 11 or 12, that is too large. So that's known
Yes,
as
sir.
numerical overflow. Numerical overflow, then numerical underflow is one other thing. So we actually cannot calculate. So we'll actually use our best guess for that. Okay.
Okay, sir.
So any question up to now? Anyone?
Sir, so if we are chopping off numbers, then we call it a round off. But if we are chopping off the mathematical terms, then we call it truncation.
Truncation, yes.
I mean, they sound a bit similar.
All of them are actually similar. In truncation error, you're truncating an mathematical expression, right? In round off, you are just truncating a value, just a value. You're rounding off some value up to another point. It is very common. You do it every day. When you are using MATLAB, you normally get up to 4, right? After decimal point, you get 4. But the actual value MATLAB calculating is 15. So it is automatically truncating. It's automatically rounding off the value. We'll see it next. Okay. Any other question?
No, sir.
Okay, so let's go into MATLAB. Sure. Okay, now the code for this one is already given in your lab manual, but I'm going to do it in a different way. Okay, I'm going to do it in a bit efficient manner. So let's focus on that. Okay. Achha. Let's come to MATLAB. First, say for example, e to the power x, I assume my x as 0.5. Okay, for our calculation. And the n value, let's take it as 10. So I will calculate up to 10. Here the x to the power n, I assume for n is equals to 10. Okay. Can you see this screen, the MATLAB?
Yes.
Yes, sir.
Okay. So let's go here. Now, so if I calculate, say for example, exp of x, okay, exp is the exponential, that is the built-in function here. Okay. As you can see, it is giving me 1.6487 up to 4 decimal point, because that is the default MATLAB. Okay. If I want to take larger, say up to 15 decimal point, I have to write format long. Okay, there are different formats available. This is the short format. If I write format long, okay. Next, if I calculate something like this, my true value is equals to xpx. Okay, and if I run it, as you can see, now you are getting 1.6487 up to 8. So this is the best approximation that we are making for now. So this is my true value. Any question up to now?
No, sir.
Okay,
No, sir.
let's start. Now we can do the start. How to calculate this form? How to calculate this one? I have to do up to x to the power 10 divided by 10 factorial. Okay. that means I can do this using a for loop. Say for example, I have to start with I is equals to 0. From this
Yes.
term 0, I have to calculate up to n, right? Up to n.
Yes.
For each value, how do you have to calculate this term? X to the power I divided by factorial of I, right?
Yes, sir.
Okay. So then int, nothing else. Simple. One thing before I do that, if you remember something that I said about pre-allocation in the last semester, pre-allocation means
Allocating the
I want
memory.
to store this one at some point, right? A of I. Say for example, yes, allocating previously. So if I actually don't pre-allocate, I just keep continuing. Say for example, at first the space is 0. Next stage, in the next iteration, I ask to increase the size of the array. In the next iteration, as I increases, I ask to increase the size of the array again. That means it is taking too much time to allocate the resources, allocate the places for this array. So this actually takes more time. But instead, I can pre-allocate it since I already know there is going to be total 11 terms, right? N is equals to 10, including 0. So there are total 11 terms. So I know the array size is going to be 11. So I can pre-allocate. Is it clear?
Sir, can you repeat this, sir? You broke in the middle, sir. So
Breaking up.
yes, sir.
Net connection is breaking up. How much did you hear? How?
Sir, we were listening. You're saying that it will just take more time if we keep on coming back. That you broke up a little bit, and then when you were drawing the boxes, sir, we show myself.
Acha. So for example, for I is equals to 0 is to n. Okay. Say for example, I want to assign a of I is equals to x to the power I divided by factorial of I.
Yes, sir.
Okay. Acha. So I have not said what is the size of the array. So I start with an int array. If I start with an int array,
Yes, sir.
that means at the first iteration, it is going to assume the first element. It is
Yes,
not going to, it has to be written I plus 1 here because MATLAB index starts with 1.
Yes, sir.
If you give 0, that is going to be error. So at the first iteration, it is going to place a value here. This is the size of A.
Yes, sir.
Acha. In the next iteration, when I is equals to 1, it is going to place A of 2. So the first one, the second one.
Yes.
Initially, it started with one element, nothing, inside nothing. In the first iteration, it placed size. In the next iteration, it is increasing its size.
Yes, sir.
In the third iteration, it is increasing its size again. Okay. You are keep increasing the size of the array at each iteration. When you do that, MATLAB is asking to allocate some resources again and again and again. Okay. That is going to take some time.
Okay, sir. Yes, sir.
Okay. So the problem can be solved is like this way. So say for example, in the final, you need total 15. Instead of doing that at the first, I define an array of 15 size. Okay.
Yes. Yes, sir.
Then at each iteration, I just place the value here, place the value here. In that way, I'm not creating again asking to increase the size. My size is fixed. Okay,
Yes.
is it clear?
Yes, sir. Yes.
So this is known as pre-allocation. And it is especially when you are doing numerical methods, you will see later on some of the numerical techniques is taking 2 hours or 3 hours to run a single code. Okay.
Sir.
It is taking 2 or 3 hours because you are not doing it properly. Okay, if you use this kind of techniques that like pre-allocation, vectorization, then you will see that your runtime has decreased a huge amount. Okay.
Okay.
So what you can do, so for example, a is equals to how to pre-allocate I is the zeros. I think there is e zeros of one array. Take 1 comma how much n plus 1, right? There are total
Yes.
11 elements.
Yes.
Okay, if we create it here, let me know if I break again. Okay, my Wi-Fi is actually making some trouble.
Okay.
So this is my initial array, total 11 array, all are 0. Now what I can do for I is equals to 0 is 2. I take one step at a time. Okay, so since I'm taking one step at a time, I don't actually have to write 1 if I'm taking one step. That is the default. Unnecessary up to n. Okay, what is my calculated value? Say for example, b is equals to, that is my x to the power I divided by factorial. Factorial is a built-in function. Factorial of I. Okay,
Yes, sir.
this is the current value, and I add it to my a of I plus 1. Again, I is starting from 0, but my MATLAB index starts from 1.
1.
So the first one goes to the first element. So I use I plus 1. For 0, I place it at 1. For I is equals to 1, I place it at second position, second index. Okay,
Yes, sir.
is equals to b, which is done. Okay, let's see the array, how the array becomes. Okay. As you can see, this is the value calculator. This is each of the term. Each of the term here, x to the power 0 divided by 0. That means 0.5 to the power 0. Something to the power 0 is 1. Divided by 1 factorial is also 1. This is the first term. The second term is 0.5 to the power 1. That means 0.5. Okay. So as you can see here, the first term was 1. The second term is 0.5. Third term is 0.125. This way, each of the term, as you go further and further, the value is decreasing and decreasing, right?
Yes,
Are
sir.
you with me so far?
Yes, sir.
Everyone?
Yes, sir.
Yes, sir.
Okay. So one thing actually remaining is the summation. I have to sum how much summation I make. If I sum up to 2 points, so this is the value up to n is equals to 2. Our approximation up to n is equals to 2. If I sum up to third point, then approximation up to n is to 3. If
Yes,
I
sir.
sum all of those things, that means approximation up to n is equals to 10. Is it clear?
Yes, sir.
So how can I do that? There is a built-in function that is cumulative summation. I sum this one with this one remaining the same. Then this one is the summation of previous one and this one. Third one is the summation of previous one and this one. If I do it like this way, so say for example, go higher, AA is equals to cumulative summation of A. If I do it like this way, 1.5 summation with the previous one. Then third one, 1.5 plus 0.125, 1.625. Okay,
Yes, sir.
so cumulatively summation. Now, as you can see, so if I say that n is equals to 4, that means I have to take up to this one, right?
Yes, sir. Yes, sir.
And the difference between this true value and this value is our what? Our error, our
Error,
true
error.
error. That is our error.
True.
Or you can say this is the truncation error. Okay.
So, Manu sir, we will choose it at our own convenience, whichever
Yes, yes.
one we want to choose up to.
Yes. Our
Okay,
true
sir.
value was calculated up to, say for example, that was calculated by MATLAB up to 15 decimal point, right? I'm assuming this one as my true value. Then up to any value of n, I can see what is my true value for any value of n. So if I write something like this, so that is my true error. True error. Can you see?
Yes, sir. Yes, now we can see. Yes.
True error. I have to buy the net package. I have not my mobile. True value minus AA. Okay. So if I do it like this way, from this value I am subtracting all of this one at a time. That is the broadcasting operation. Okay.
Yes, sir.
Run this one, as you can see, when n is equals to 1, your true error was 0.648. For n is equals to 2, the error was 0.148. As you going further and further, the true error is decreasing and decreasing. Right?
Yes, sir.
Any question up to now, anyone?
Sir, could you explain this procedure again?
Which portion? This one?
So after the loop, like after the cumulative sum of A.
Oh, that's a true error. So now, say for example, I have found the value A, say for example, it was initially 1. Okay, then it was 1.5 up to second iteration, then it was 1.625. Okay, then it was 1 point something, a little bit higher.
Yes, sir.
This was my up to n is equals to 1, this was n equals to 2, this was n is equals to 3. Okay, what I'm doing here, so our true value was something I actually created from, taken from MATLAB, the actual value. So this was my true value, 1.648, this one. From this one, from the true value is, sorry, my ET, that is the true error. My true error was calculated, this true value minus this A. Okay, that means I have true value, say for example, let's write it like this way, 1 point, that is my true value, VT. Okay, this is my single value. From this one, I am subtracting A. From one value, I am subtracting a vector, right? 1, 1.5, 1.625, like this way, right? Up to 15
Yes, sir.
digits. Okay. So when I am subtracting from one value, I'm subtracting all of this thing. It will perform a broadcasting operation. It will broadcast itself to all of this thing. 1, 1, 1, 1. Then for
Yes, sir.
each pair, it is going to subtract and give us a value for each pair. Okay.
Yes, sir.
So for each pair, I'm getting the value. I'm getting a value here. This value, this value, this value. So each of them is my ET for nth term.
Yes,
Are
sir.
you getting me?
Yes, sir. Yes, sir.
So for each value is, each one is my value or my approximated value for up to n. Okay.
Yes, sir.
So this is my true error. Now, so let's go here. Okay. So how to visualize it? It is also important that I try to visualize this thing. Now you can visualize it writing a code. Okay. You can visualize it writing a code. Or you can do it, you can in MATLAB, you can do it directly. As you can see, first go to the workspace. Okay. Which one I want to visualize? I want to visualize the true error. So I click this one. Are you following me?
Yes, sir.
Okay.
Yes.
Then you can see there is option plots, right? Go to the plot
Yes,
option. And what I want to plot, I want to create a line plot. So I click this one. This is a line plot. As you can see, 2D line graph using linear axis. So I this one, click this one. So as you can see, a line plot is created. Can you see this screen?
Yes.
Yes, sir.
So what is happening here? First, the error was 0.7, almost 7. Then it was 0.15. Then it is 0.023, right? The error is decreasing. As we
Yes.
increase the n, as we increase the number of iteration, the error is decreasing. And from this figure, as you can see, first the error was this. At each iteration, the error is decreasing, right?
Yes.
So this is your figure. Now, the figure needs some names. As you can see, there is an insert tab, right?
Yes.
The X level, what does, if you click on the X level, there is a pointer is coming. That is the number of iteration.
Iteration.
That is the number of iteration. Again, you can insert an Y level. What is the Y level? That is my true error.
Value.
Okay, it is automatically given here. So always use this one. Otherwise, the figure does not have any value. No one will understand what is this one right here. You can also add some title of this one. There is legend. Legend is even when there are multiple lines. Okay. Go to the file, then there is save as, right?
Yes, sir.
In the save as, if you go here, okay. As you can see, it is automatically saved as figure type, MATLAB figure. But
Yes.
if you save it as MATLAB figure, you will not be able to see it without MATLAB. There is other formats like PNG format or JPEG format. Save it like this. Then you will be able to use it outside MATLAB. Okay, in another format. You can also export the figure like this way. Okay. Anything, any question up to now?
No, sir.
Okay, as you can see, when I was doing that, if you look at the command window here, the plot, I didn't write this one. It was automatically created, right?
Yes, sir.
I didn't write. So when you're doing it, the command is automatically given here in the command window. MATLAB does it automatically.
Yes, sir.
Okay. Achha. Now, any question up to now? Anyone?
No, sir.
Achha. The problem with this approach is that, say for example, for I is equals to 1:n, I am performing a routine here. Whatever I was doing, this is you can say simply a routine. Okay. So for each of the value, you are doing this. Okay. So when you have n is equals to 10, that is simple. When you have n is equals to 1 million, that means you have to perform the same routine 1 million times. So the time complexity of your code increases how? Linearly, right?
Yes, sir.
Yes, sir.
So if you try to plot a graph here, I plot a graph here like this. This is your n. What is in the y-axis? The time complexity that is represented as big O of n. Okay, that is known as big O notation. Okay, big O notation. This is a qualitative analysis to analyze the time complexity of your code. So when you have like this kind of loop, one loop, what do you have? You have a linear
Complexity.
linear. That means as the n increases, the time complexity increases linearly. Okay. For 100, it is going to take big O of 100. For 1 million, it is going to take big O of 1 million like this. So as the n, the size of your array increases, the time complexity increases. What if you have inside the routine, you have another for loop? Say for example, if you had another for example, for z is equals to, again, 1:n. You have inner for loop. It was doing another task. Okay.
So it will be, oh my
Slope
God.
will be more.
Okay. So then you have two for loop. For each value of I here, it is performing this one.
So n to
For
the power
one-
n. Yes, wait a minute.
Then for 2, again this one. For 3, again this one. For n, again this one. That means n multiple by n. So this has a runtime of big O of n square.
Yes.
Are you getting me, everyone?
Yes, sir.
Okay. So when you have something like this inside a loop, I have a nested for loop. So the runtime increases n square time. So what does that mean? Understand? So that means when you have a loop of 10, array of 10, the runtime is taking big O of 100 becomes. Okay. That is equal to when you have this one only big O of n এর ক্ষেত্রে 100, that is only 10, you are taking only array of size of 10 is going to 100, becoming 100. When you have 1 million, how much it become? Can you imagine? If you have 10 to the power 3, 10 to the power 5, it is becoming
10 to the power 10.
10. Okay, so the runtime here, as you can see for big O of n square, this was your big O of n. For big O of n square, it is actually dramatically increasing. For a small value of n, it is increasing exponentially. This is my big O of n square. Okay,
Yes.
if you have something, if you have another nested inside, that will become big O of n cube. That is even further. Okay, so for longer array, when you have a large array, so doing this for loop, it is better to avoid any for loop if you can. You will not be able to do it always, but sometimes in many of the scenarios, you will be able to do that. You will be able to avoid one for loop. Again, if you can avoid out of 3 for loop, if you can avoid only 1 for loop, the runtime decreases from big O of n cube to n square. That is a huge drop, right? That means there is a
Yes,
huge
sir.
gain in performance. Okay. So if you want to do this kind of avoiding a for loop, there is many things in middle. There are n log n, okay, other things like this, log n. Okay, there are other parameters like this. These are inside these two. So I'm not going to discuss in this one. Other one is that I can avoid a for loop using a vectorization approach.
Sir, one question, sir.
Yes, of
You
course.
said that as the arrays become larger, the runtime increases or decreases?
Increases.
Increases to the power, like the power of the
Yes,
larger.
n. N is the size of the array.
So is it a good thing or a bad thing?
It's a bad
is it-
thing. That means when you
Okay,
are
runtime.
performing operation on, if you're performing this loop 10,000 times, okay, that means it is going to take a large amount of time, right? So say for example, you have to perform this loop 10,000 times. So if you have to do it, this iterate portion 10,000 times, that's a huge, it is taking a huge amount of time for
Yes, sir.
big O of n. And inside, if it had a nested loop inside, that means 10 to the power 4, 10 to the power 8, that is going to take too long. This one becomes too large. Okay. Are you getting me?
Yes, sir. Clear.
So I cannot decrease this one, but I can use some efficient way to avoid writing the for loop altogether. Okay. Sometimes it is possible. That is the way is vectorization. If I can do that, the runtimes become like a constant amount of time. Nothing like this. It is becoming constant, almost constant. That means whether the size increases doesn't matter. The vectorization process will always take almost a constant amount of time. Are you getting me?
Yes,
sir.
sir.
So how to
Yes.
do that? How can I do that? Okay, this is simple. I have this one. I have to convert it into a vectorized way. So how to do that? So the thing I was doing here is for I is equals to 0 is to n, I am calculating x to the power I divided by, internet is unstable, y x to the power I divided by factorial of I. Are you seeing this? Hello?
Sir, you're breaking, sir. You're breaking, sir.
বিরক্ত করতেছে এই জিনিসটা। Can you see the screen? Let me
Yes.
buy a package. Okay. So can you hear me now?
Yes.
Okay, acha. So let me know if it problems again. Acha, so this is what I was doing. I was calculating for each of the term x to the power I divided by factorial of I n, right? This was our for loop, and I was doing that for all the terms. But now, say, so what you can do here is that, so I have a vector initially. I can perform this operation x to the power I. My x was 0.5. I want to perform this power operation from x 0.5 to the power 0, 0.5 to the power 1, up to 0.5 to the power n. Hello,
Hello. Yes, sir.
let me know that you are there.
Yes, sir. We are listening.
Sir.
sir.
So I'm doing this power operation one at a time, but what you can do here, I can do this, I can give this power operation inside a vector from 0 is to n. So instead of doing it one by one, it is perform this operation one at a time, not again and again. Okay, I can make the power operation only at a time. Then the factorial same. I can perform this factorial instead of performing for factorial of 0, then 1 and 2, one by one. Instead of what I can do, I can inside this factorial function, I can place an array. Then what will it do? It will perform this operation on each of the elements simultaneously, parallelly. That is known as parallel computation. Okay,
Yes.
that is parallel computation. Parallel computation. Okay. So let's see how to do that. Okay. Simple thing. So here we had calculated this one. Let's come. Yeah. A B is question. Acha. Let's start first. P. Acha. Let's get a vector first. Vector is equals to 0 is to n. That is my vector that I used to take 0 is to n. Okay. I take a vector, get a vector 0 is to n. All right.
Yes, sir. Yes. Yes.
Then first term. So that is the numerator term is equals to, what is my numerator? X to the power. So when I'm using, instead of element, when I'm using a vector, I have to use a dot sign. Dot to the power of this vec. Okay.
Yes, sir.
If I do that, see what happens. So 0.5 to the power 0, that is 1. 0.5 to the power 1 is equals to 0.5. 0.5 to the power 2 is equals to 0.25. Okay. So this is performing this operation with the vector all at a time, all at the same time. Okay. Then comes the denominator. What is the denominator? My factorial. Factorial of this vector. Factorial of 0, then 1, all at the same time. So factorial of 0 is 1, factorial of 1 is 1, factorial of 2 is 2, 3 is 6, 4 is 24. Okay.
Yes, sir.
Now
Yes,
what we have to do? I have to divide the numerator with the denominator, element-wise division, right?
Yes, sir.
So basically what I'm doing here is that my original array was like this, e to the power x equals to x to the power 0 divided by 0 factorial, then x to the power 1 divided by 1 factorial, then x to the power 2 divided by 2 factorial, like this. So first I calculated a vector numerator of all this term like this, x to the power 0, x to the power 1, x to the power 2, okay, up to x to the power n. Okay, up to x to the power n, all at the same time. I have created another vector of this factorial, 0 factorial, 1 factorial, 2 factorial, 3 factorial, like this.
Yes, sir.
Then what I'm going to do, I'm going to perform this element wise division, right?
Yes, sir.
Okay. So if I do that, so yes, numerator, denominator, that is my true error. That will become now, that will become my So let's name it P is equals to numerator. Point-wise division is represented as point then slash. Okay. Element-wise division. So now as you can see, this is my 0.05, 0.125. That is same as A that you previously created using this for loop, right?
Sir, in the 15 number line, sir, when you wrote x dot to the power vector,
Yeah.
it is to do this element wise, we gave that dot, right, sir?
Yes, yes. To
Okay.
perform element wise, I gave this dot.
Okay, sir. Okay, sir.
Okay. So as you can see, this was the A that you calculated using the for loop. This is here is the mark here. And this
Yeah.
is the P that we calculated here. These are the same, right?
Yes, sir.
So instead of writing this for loop, I have done this one like this, using calculating numerator, calculating denominator, and vectorizing like this way. Okay.
Yes, sir.
So this is actually for a small area. So we are calculating for 0 to n. You will not see the difference. But for some other term, when you have n is equals to very large, like 1 million, like this, then you will see there is a huge gain in performance. You can check. Don't check with the factorial, because if you calculate factorial of 20, your numerical, there will be a numerical overflow. You cannot do that. Factorial 20 is very large. So P is equals to like this. The only thing is remaining is I have to take the cumulative summation, right?
Yes.
Cumulative summation of P. Then at each point, I am getting the value. The value is gradually increasing like this. So if I do like this, Q, go to the plots and plot it. As you can see, this is my plot. My
Yes, sir.
true value. So I am plotting this one like this way. So gradually my true value was 1.64877 like this. As you can see, gradually it is going that way, right?
Yes, sir. Yes, sir.
Gradually going that way. I think we can do one other thing. Hold on. Okay, I have to check it. I will check it later, then show you. You can also add a line here. Just add a line and see it later. Also add a insert. Okay, always insert this one. One other thing. Let me show another thing. When I was calculating the true error, so I was plotting it like this way. As you can see, in the y-axis, the value here, you can barely see it here, right? Because the difference is too large, so it is difficult to see. In scenarios like this, you can create a semilog plot. The semilog plot, you can see here, there is semilog x, then semilog y. Can you see it?
Yes, sir.
The semilog y means I'm using a logarithmic scale in the y-axis. So if you do this, as you can see, this is still the number of iteration, but this is the logarithmic scale, right?
Yes.
Start y level, that is the error. What is the error? At first iteration, the error was 10 to the power 0. That means close to 1. In the next iteration, it becomes 10 to the power minus 2. Third iteration, it is becoming like this. Now the error is in the logarithmic scale. So the visualization is much more clear how the value is decreasing. When you
Yes,
go
sir.
to up to 10th iteration, okay, as you can see, the error is becoming 10 to the power minus 10. That is too small. Okay, that you cannot visualize on a direct linear graph. Is it clear?
Yes, sir.
Yes, sir.
You can also you can check here. You can also create other plots like this from this way. You can also create subplot from this one. Okay, you can try it by yourself. So any question up to now? Anyone?
No, sir.
Okay. So first, what we did it using a for loop. Then you saw how we can actually remove the for loop using this vectorization operation. Okay. Then the thing is actually similar. So up to this one, in your lab manual, it is done in a different way. You can also try it by yourself if you want. And at the end of the lab report, there is a task given, sin f and cos x for that. This will be your lab assignment for this week. Okay, try to do it by yourself. And there is a lab task. I'm not giving any lab tasks today, but in the upcoming labs, I might give you some lab tasks. Okay. there will be some lab performance mark based on that. Okay. So any questions up to now?
Sir, in the factorial, you said if you use it, there will be a numerical overflow for high numbers.
Yes.
So how to avoid that?
There is nothing you can do to avoid that, because factorial 10 is already a very large number, right?
Yes, sir.
Factorial 10. If I calculate factorial 10 value, I calculate factorial 10 sorry. So it will go up to bit much. There is a limitation of how much it can represent MATLAB. In Python has a long integer. Okay. Python supports a huge integers, so you can try it Python. Python you can calculate higher number of factorial. In MATLAB, by default, you cannot actually do. There is symbolic math toolbox. Using that toolbox, you can actually go for higher and higher value, but there is a limitation for normal use. Okay.
Yes.
So you can try it in Python, see how far it can go. Python has a long range. So any other question? If not, so if you do not have any question, then you can leave. Okay.